side. And then we do the derivative with respect to x on the right side. All right, carefully. What's the derivative of sine of something? Cosine. Times, now the derivative of what's inside, right? So what's the derivative of x with respect to x? 1. Plus, what's the derivative of y with respect to x? dy dx, right? dy dx. And then equals, over here, we take derivative of each of these separately because there's subtraction. What's derivative of x squared with respect to x? 2x minus what's derivative of y squared with respect to x? 2y dy dx. That's the one that everyone misses right there. What's happening here? Y is the derivative of y squared. Y is the derivative of y squared with respect to x equal to 2y dy dx. Why is that? Because we're using chain rule. You have something squared, right? What's the derivative of anything squared? 2 times that something to the first power, right? Chain rule says times, now the derivative of what's inside. What's the derivative of y with respect to x? dy dx, right? Not 1. That's why it's 2y dy dx. This is a reminder of what we had to deal with in Cal 1. I've got marker caps all over the place here. All right. Yes? Now, I mean, we would have to go and get dy dx by itself on one side of the equation, but this is just the mechanical part of this is called implicit differentiation. Who had me for Cal 1? Anyone Cal? Do y'all remember the story about the girl?
Yeah. I was thinking about it already.
Yeah, you were just thinking about it. Okay, yeah. So I'm just wondering if you remember that. It's a long story. Maybe I'll tell it later. Let's get through this. No, I will. I'll share it. I mean, but let's do an example first. I'll share it when we're done with the example. Okay, so look. So we're given an equation, right? And look at what we're asked first. We're asked to find the partial of z with respect to x. All right, could you take this equation and solve it for z? Maybe. I mean, maybe you could. Algebraically, it might be a nightmare, but you might be able to get z by itself, right? You might. But I could give you another equation up there where you can't get z by itself. So we need a method of finding the partial of z with respect to x without actually having to solve for z. So I'm going to use implicit differentiation. Now pay close attention. With this notation, I am saying that z, right, is a function of more than one variable. I'm going to treat the x like a variable, and that means that the y is going to be treated like a constant. All right? Remember that. That's what that notation means. I'm saying z depends on 2 different variables. How do I know 2 different ones? Look at the equation. How many variables are in here? 3. If I'm taking derivative of z with respect to x, then I'm saying z depends on x and y. I'm going to treat x like the variable and treat y like the constant. And I want to know what happens. Okay? So to do this, I'm going to take the partial with respect to x on the left side of the equation. See, this is just like implicit in Cal 1. And then equals now the partial with respect to x on the right-hand side of the equation. So exactly what we just did in the previous problem, except we're doing a partial with respect to x, partial with respect to x. The only reason we're using that notation is because there's a y in here as well that we're holding as a constant. And so now, because there's a bunch of addition in here, I'm just go term by term. What is the derivative of x cubed with respect to x? 3x squared, and that's it, right?
Yeah.
3x squared. Yes?
You want those like dy dx's? You wouldn't have like a dz dx?
No, it's with respect to what though, right?
Oh,
So
okay,
yes, I wanted to point this out, that what we're doing, we're taking the derivative of something cubed, right? What's the derivative of something cubed? It would be 3 times whatever was there squared. What was there? X. Now, times the derivative of what's in here. What's the derivative of x with respect to x? That would be the derivative with respect to x of x. And the fact that it's partial really doesn't matter. That's just to keep me remembering that y is held constant. This is still 1, which is why you don't have anything there. Okay, so the derivative of this with respect to x is 3x squared plus derivative of y cubed. 0. Why? Because we're holding y as a constant. So this is just some constant. 0. Plus, drum roll, 3z squared, power rule. But again, it's more like the chain rule here, isn't it? So you bring the 3 out, z to the second times now the derivative of z with respect to x. And what is that? Well, shit, I don't know, but that's what I'm trying to find, right? It's the partial of z with respect to x. That's actually what I'm trying to find in this problem. So the fact that it pops out is pretty good, right? Okay, plus, oh crap, now we have an issue. Because this right here contains constants, but it also has 2 variables, doesn't it? Like z depends on x and y, but x is our independent variable, y is a constant. Let me write that a little different. Do you all agree that that's 6y times xz, right? That's the same, right? And this is a constant, isn't it? That's some constant. So if I take derivative, right, when I take derivative of this piece, that constant right there comes for the ride, yes? So I'm just going to put it here, 6y. Now, what's next to it? The derivative of this, which is a product rule. And you're going to need that product rule to be in parentheses because you're going to get 2 terms from it, and the 6y will have to distribute to each of those terms. That's one way to do it. Another way to do it would be just to, go 6yx times z and do a product rule like that and treat that as your first one, this is your second. Either way, I mean, you should be comfortable doing it both ways.
Can you explain?
Which way? This first way?
Yeah.
Okay, this right here, I just rearranged and I put the 6y together because I know y is a constant. Do you agree that if I ask you to take derivative of this, if that's a constant, that's just going to come for the ride? There we go. There it is. Now, I still have to take derivative of that, though. And that's going to be a product rule. And because I know product rule is going to create 2 different terms, I went ahead and put that in parentheses to prepare for the product rule. Yes? Now, let's do the product rule. What's the derivative of the first one with respect to x? 1, right? 1 times z plus, now the derivative of the second one with respect to x, partial z with respect to x times x. And then equals? 0. Derivative of 1 with respect to x is 0. Yeah, in any calculus class you ever take, the derivative of a constant will always be 0. Like that will never change no matter what class you ever go to. Right? Because if you have a constant, right, the derivative means what's the rate of change of that constant. And constants don't change. That's the definition of a constant, is that it doesn't change. So the change is 0. Rate of change is 0. All right. There it is. Now, we're done as far as the algebra, but you see that and that? That's what we were trying to solve for, right? You could now algebraically move things around and isolate the green boxes on one side of the equation, and then that would be your answer, all right? And whatever that answer is represents what? I'm trying to see if you can wrap your head around what that would mean. Like whatever this, solve for this, and you get some expression, what does it mean? It means it's a derivative of z with respect to x. So what it means is that if you take this equation and you change x just a little bit, okay? Just give me some value of x and then change it just a little bit, just nudge it just a little bit. How much does the z change by? Okay? That's what it's going to tell you. But you have to be holding your y constant while you're doing that. So if you imagine holding your y constant, if I change the x just a little bit, it should have an impact on the z. And this measures that rate of change. All right, what do you think about the next one? The only difference there is it's with respect to y, right? Okay, let's see if we can go through this one a little faster. So I'm going to do implicit. I'm going to do the partial with respect to y. It's almost the same, right? Almost the same. What am I holding constant this time? X, okay. All right, hey, the right side's 0. Yes. Everyone's going to get that right. Okay, now this part, partial of, I'm holding x constant, right? So that's 0. Okay, this derivative with respect to y. 3y squared, and then you could say like dy dy, which would be 1. So you don't need to put that there. And then you have this, 3z squared. You do need the partial z with respect to y. And basically the same thing, except this time the 6x is the constant, right? The 6x is the constant, not the 6y. So put 6x and then parentheses, little product rule in here. Derivative of y with respect to y, 1 times z, plus derivative of z with respect to y, partial z with respect to y, times y. All right, I hope that all makes sense. The second one is saying if we take that equation, fix the x, and then nudge the y just a little bit, it'll give us the rate of change of z. So the story, and I'm going to make it very short, very short. When I was in graduate school, I would go out to clubs like once a month just to like let it all go, because all I did was math. Like I slept it, ate it, everything I did was math. And so I didn't have a social life. So I'd take a cab to this club and I would just get crazy, like once a month, just get nuts. And so I like to dance, right? I get out there, sweat all that stress out. And you know, you're out dancing. I wouldn't even go with friends. Like I didn't have many friends. I just went out and just go out into the middle of the dance floor and dance, right? So inevitably, I would meet somebody, they would come up to me. I never approached anyone because I didn't have time for it, right? So if a girl came up to me, okay, this is so dumb. This is so dumb when I think back on it. The first question I would ask her is what the derivative of x was. And the reason why is because I didn't have time for any social, like I didn't have time. So if there was going to be any conversation that I would find meaningful, then it's going to have to do with math, all right? It's going to. So I'm out at this club, dancing. And now trust me, I didn't get to use this line very much, okay? But when I did get approached, right? So this girl comes up to me and I ask her, and it's like it's loud and we're dancing. We had been dancing, sweating. I went to the bar, she followed me, started talking to me, and I kind of leaned over into her ear. I was like, hey, what's the derivative of x? And her response was, with respect to what? And I was expecting 1, right? I was expecting derivative of x is 1. That's what I was expecting, because you would assume most people would think when I say derivative of x, I'm saying with respect to x, because that's when you learn it, that's the way you learn it, right? And then later on, you learn about implicit, and you learn that the independent variable matters, and you have to be specific about what you're differentiating with respect to. So she was like, with respect to what? And I'm like, holy shit, you know? Anyway, so I tell that story in Cal 1 as a point. The point of that story is that it matters with respect to what, right? Like it matters. Like the derivative of this is 3y squared. Why? Because we're differentiating with respect to y, right? It matters. And obviously it stuck. You remember the story, right? That's why I tell the story, because it sticks usually with people when I tell it that way. So anyways, people ask me, did you marry her? It's like, no, I could never marry someone who thinks like me, ever. Ever. I need the opposite. Thank goodness I have the opposite. All right. There it is. That's the end of that section. This homework that's up here is usually more accurate than what's on the calendar. So if you ever see any discrepancies, just do this. But really, the homework is really just practice for you to just get comfortable with these ideas. All right. How are we doing time-wise? 12:22? Yeah, I think we can talk about. Where are we on the calendar? I feel like we're ahead.
We're caught up now, yeah.
I feel like we're ahead, but did we fall a little bit behind? I told y'all there's no such thing as we're ahead. Let's take a break. We already lost a day with a holiday in here, right? So
I think today's was just special practical.
today, right? That's where we are. No, partials, right? Partial derivatives. Okay, I say we go for tangent planes. I say we go for it. It's a short section. It's a formula. You apply the formula, we're done. If we can spend 2 entire days on Lagrange, that would be wonderful. Usually I only get 1 day for it, but if we could spend 2, it would be so good. So let's go for tangent planes today. I believe I even had it up, ready to go. No, did I?
Yeah, it's the
So
next
11:4. Oh, there it is. Okay, so naturally, from what our discussion of this earlier, last class, is that if you have a surface and you have a point on that surface, it makes most sense to talk about the tangent plane to that surface at that point, as opposed to a tangent line. Right now, what we've been able to do is say, okay, like fix one variable, find the slope of tangent line, fix the other variable, find the slope of tangent line, but how can we combine those together to give us a plane, right? And it turns out it's freaking so easy to do, it just doesn't even seem like math should work this way, but it does, all right? So this is the actual formula for it. If somebody hands you a surface, okay? Z is some function of x and y. And it has continuous partial derivatives. All that means is that the surface you're looking at, when you take the partials, it's not some crazy shit that you can't graph. Like the partial derivatives are nice. They're well behaved. Then the equation of the plane, which is tangent to that surface at some given point, x naught, y naught, 0, is, well, it's a plane, right? What's the generic equation of a plane? Ax minus x naught plus b times y minus y naught plus c times z minus z naught. That should be old news to you, right, by now? That's the generic equation of a plane, where x naught, y naught, z naught is a point. And A, B, C is the what? Yeah, that's the direction. Well, it's the components of this vector that's called the what vector of that plane? The normal vector of that plane. The coefficients out here are just the components of the normal vector. This note says, guess what? Do y'all see that formula right here? Do y'all see that formula? This is the A, this is the B, and this is the C. The formula says that if you want to know what the normal vector is of this plane, the A is the partial derivative of that function with respect to x at the point x naught, y naught. The B is the partial of that function with respect to y at that x naught, y naught. So that's like you're getting those two slopes, right? Those two slopes are your direction vectors, okay? They're the components, the components of your direction vectors, right? And then your C is always -1 if you're dealing with a function of two variables like this. I will explain that later because we're going to have another note in another section where we can do this same thing, but this is no longer has to be a function. It can be like a quadratic surface. That, you know how these have to pass like that vertical line test idea? Later on, we won't need that requirement anymore, and we'll have a formula, and it'll make more sense why this is -1. For now, you can just look at it as your normal vector. Your z component just always points straight down. Your z component only points straight down. All right, there it is. So we should be able to do that pretty easily, I think. So here's a surface, f of xy equals 1/2 xy. This is a picture of this surface, just so you see it. That's the surface right there, okay? And what I'm trying to do is, or what we're trying to do here is we're trying to go to this point, 1, 2, right there, that point right there in black, and we're trying to find the equation of the plane that's tangent to that surface at that point. So we're trying to find, whoa, what the heck? Where'd it go? There it is. Did y'all see that plane? We're trying to find the equation of this plane, this green plane. And so in order to do it, all we need to define a plane is a point and a normal vector. Right? So the point we're going to get from the x and y coordinate, you'll see. Let's do it. All right. So what do I need to do this? Partials, right? Need some partials. So what's the partial of this with respect to x? Oh man, this is going to be pretty simple, right? What's the partial of that with respect to x? 1/2 y. Okay, what's partial of that with respect to y? 1/2 x. Okay. 1/2 x, 1/2 y are the two partials there, or 1/2 y, 1/2 x. Okay, so the formula, which I could just scroll and show it, but I'm going to write it again. The formula for the equation of the tangent plane is the partial of f with respect to x at the point x naught, y naught, in front of x minus x naught. So that's our a in front of the x minus x naught. And then we have plus the b, which is partial of f with respect to y at x naught, y naught, in front of y minus y naught. And then it will always be minus 1, and then z minus z naught equals 0. So that's our generic equation for the tangent plane. What does this mean? I take this and plug into it what values? 1, 2, right? 1, 2. So I want to take this right here, and I want to plug into this 1, 2. 1 for x and 2 for y. Well, there is no x in there, right? So this should just be 1. Okay, and then we also need this one, partial of f with respect to y at 1, 2. And what's that going to be? 1/2, replacing x with 1. And look, that's it. That's it. We can plug everything in now. Our equation is this, which was 1. X minus 1 from this point right there. That's x naught. That's y naught. And this is z naught. So this is x minus 1. And then plus this, which is 1/2. And then y minus 2. And then minus 1. And then z minus 1 equals 0. And that is it. That is the equation of the plane. Shouldn't be that easy, huh?
So the normal vector would be 1.
The normal vector, yeah. The normal vector, if you wanted to identify it, the normal vector would be the vector 1, 1/2, -1.
And it's always going to be -1.
Always -1 if you're looking at f as a function of x and y.
Okay.
Yep.
So if it was like f as a function of
Y and z,
or y and z,
then whatever variable's not there would be the -1. Uh-huh. All right. Yeah, we only have 2 examples and we're done. Why don't you try this one? Why don't we make this? We still have about 10 minutes or so. Why don't you see if you can? It's the same exact thing. It's just this derivative is a little harder.
Isn't that like 1 over?
All right, well, you go figure it out. All right, what I'll do is I'm going to step out for a minute, and then when I come back, I'll take a volunteer or several volunteers. Or if you're feeling real brave, just go write the equation on the board somewhere. Grab a marker, and if you can get the equation of that tangent plane, put it up on the board. You know what you're supposed to do? Do y'all want the formula up here? Yeah, I'll put the formula, I'll put it over here. The formula for the equation of the tangent plane, right?
Yeah.
Okay. There you go. What is arctangent of 1? You should be able to tell just by this. If this is 1, well, that's what you get when you plug in 1 and 1, right? 1 and 1. So arctangent of 1 should be what? Pi over 4. But you should also know that from pre-cal, right? Like, or arctangent of 1 means at what angle on the unit circle between negative pi over 2 and pi over 2 is the y coordinate divided by the x coordinate equal to 1? That's root 2 over 2, root 2 over 2, which is at 45 degrees, pi over 4. Okay, just let's go. I'll leave it on. Anybody having trouble? I can come and help you with the derivative. Yes. Start with your partial. Okay. Yep.